So today I'm going to talk about heat conduction in 1D and 2D micro nano systems, which is a non-equilibrium statistical problem from microelectronic chips. So I'm currently affiliated with Department of Material Science and Engineering, Department of Physics, and the School of Microelectronics. So the two objectives of this talk. First one, I will show you that this is actually an engineering problem in the semiconductor industry. The second, this is a fundamental problem in non-equilibrium statistical physics. So we know that this is a Moore's law for a semiconductor industry. So the number of transistors going up from a few thousand to now it's about more than 10 billions per chip. So the power density goes up to almost to 100 to 200 watt per square centimeter. For some hotspot power density, which is a 1,000 watt per square centimeter, which is about 10,000 times of sun's power to the Earth's surface. So the heat problem becomes a very big issue for microelectronic chips. This includes actually for this 5G communication, for consumable device, and for electric vehicles, batteries, and so on and so forth. So if we look at actually how the heat goes through the chips from chip inside to the outside, which usually we have a chip here, and then we need a thermal interfacial material one to get the heat from hot spot to the heat spreader. So which means to make the heat more uniform in this spreader. And then from a spreader, we need another thermal interfacial material two to get heat out to heat sink. So this is actually usually the typical actually electronic packaging used in nowadays electronic devices. So from between, for example, the spreader to heat sink. So we have a heat going from heater through the thermal interfacial material to heat sink. So here we have two interfaces here and there. And inside the chips, we have the heat generator. For example, this is the third generation of band gap or power semiconductor new devices, which it generates heat from nitrogen gallium, and it goes through the barriers and the C-doped gallium nitride and so on and so forth. So the heat goes through from different layers. So this is inside the chip. Inside chip, there are actually metal layers. Sometimes it's even more than 100 layers. So the heat will go through one layer to another layer, and these kind of things is a kind of one-dimensional heat conduction. We can simplify it by one, for example, the atom interact with a spring with another layer. So this can be simplified as a one-dimensional heat conduction. And then, of course, inside one material, for example, like let's see in the nitrogen gallium, then heat, for example, generate inside in the middle can separate to the outside inside the one layer. So which means it's in plane. So this is kind of a 2D material. So this actually the motivation from our side from 1D and to 2D. So 2D, which means inside a layer like graphene, and then 1D is like through the different layers. This is perpendicular to the different layers. So this is my talk. First part of my talk, I'll go through the heat conduction in 1D system and 2D system, and then the second part will go through how the heat goes through from one layer to the another layer, because we have an interface here for realistic material, because the thermal resistance in two different layers are different. So which means you have an interfacial thermal resistance. So some of the work I will report it here are summarized in the several recent articles. The interfacial thermal resistance published in last year in 2022, and the thermal conduction in 2D material was published in 2018. So in my talk, I have some new results since 2018, including, for example, twisted graphene, twisted bilayer graphene. So actually for statistical physics problem, the question is for a given Hamiltonian. For example, this is 1D or 2D, we can write down the Hamiltonian. We have interparticle potential and plus on-site potential. So we have a couple of questions to answer, whether the steady state exists or whether the steady state is unique. And we need to answer how fast we can reach the steady state. And then we will answer the question whether a temperature gradient can be established. And the last question to be answered is, can heat flow follow Fourier law? So actually, the simply model is a one-dimensional harmonic chain. So this model can be actually rewritten in momentum space, which has a non-interaction phonons. So because no interaction between phonons, so which means there's no heat resistance. So no heat resistance means no temperature, no temperature gradient can be established. So this was the work, analytic work proved by Baowen Li et al. In 1967. And then actually George Parisi in 1997 has given a very nice work, proved that for a nonlinear one-dimensional oscillator, so if G goes to 0, so which means the time to arrive equilibrium diverges when G goes to 0. So this actually question tell us it is impossible to numerically calculate, for example, this one-dimensional heat conduction problem for harmonic oscillator. So the heat conduction problem start from FBU model in 1993 from two Japanese colleagues. So they studied this FBU beta model. So this is the result they discovered. From this, they had the first one on the left is a temperature gradient. The right one is the semiconductivity versus the number of lattice. So it's interesting, from this plot, it looks like what the thought is that when n goes to bigger, so this one should be saturated. So they didn't draw log kappa log n. So from this normal kappa versus n, they found the conclusion that FPU model has a finite semiconductivity. So since changes when in 1997, when Lepre and the three colleagues they restudied this problem and found that the draw the semiconductivity versus n, here they go a draw line, a linear line, which means kappa versus n in this power law. So which means FPU model has a divergent semiconductivity. So in 1998, we studied this very general Hamiltonian, which is Franklin-Condorcet model, which includes interaction potential and also on-site potential. So the on-site potential plays a very important role here. With the on-site potential, in general case, there exists a gap. This gap means that the lowest frequency is non-zero. It's different from FPU. FPU model has a momentum conservation, which means that the translational invariance, which means that the lowest mode is 0. So this FK model has a non-zero lowest mode. So from numerical calculation found that FK model has a finite semiconductivity, which is different from FBU model, which is divergence. So the temperature dependent semiconductivity also changes from FBU one is decreases when temperature increases, and FK model increases when temperature increases. So since 1998, so this problem becomes very hot, and this research area becomes very active. And if you look at actually the papers published every year, I must see that so far more than 1,000, even probably 2,000 papers every year. It's about 50 to 100 papers. So here are some actually examples from real materials. So like nanotubes, which is power law divergent with 0.32. This from Maruyama's calculation. From my group's calculations around 0.4, and from silicon nanowire, which is at room temperature is about 0.27, at high temperature is 0.15, and the polymer chains also around 0.4. And also experiment works like nanotubes, which is around 0.6, 0.5. This is a carbon nanotube, and for boron nitride. And the carbon nanotube one, Professor Zhang and his group in Taiwan extended to a very, very long nanotube, very thin. Diameter is 2 nanometer, and the length goes to 1 millimeter or 2 millimeter. So from 1 to 3 to 9, the 9 samples all show divergent thermoconductivity. And very good 2 recent experiments from the Li's group. This one published in Nature Nanotechnology in 2021. They studied different diameters, nanowires, very, very thin, diameter from 8.5 to 158 nanometers, all shows divergent thermoconductivity. And this is for the 10.6, 12, and 12.3 nanometers, and they show very close to kappa versus L with exponent 1/3. And another work, which is for thin film, but the measure thermal conductivity in perpendicular in perpendicular direction, which means the heat conduction in one direction. And here they show the thermal conductivity versus thickness of the thin film with the power 0.26. Yeah. So now we have so many numerical as well as experimental results show that in one-dimensional system, thermal conductivity diverges with the system length. The question is, what is the underlying physical mechanism? So the first, a little bit rigorous proof was done by Poussin and David Campbell in 2000. They proved that if you have a momentum conservation with U equals 0, which means you have anomalous energy transport. So later on, my group have has worked out some connection with anomalous diffusion. So the first one we obtained from this actually we get a connection between anomalous diffusion with anomalous heat conduction. We got actually a kind of connection between these two phenomena. So which means for normal conduction we have a normal diffusion, we have a normal conduction, which means the Fourier law. This is what we know that in the undergraduate textbook. And for super diffusion, we have a divergent thermal conductivity. For ballistic motion, we have ballistic beta equal to 1. For subdiffusion, we have a kind of a 0 thermal conductivity. So we start from this kind of fractional differential equation by using the main first passage time to obtain this connection between this diffusion exponent alpha with a divergent thermal conductivity exponent beta. So we obtain this very simple formula, which is beta equal to 2 minus 2 divided by alpha. So this is actually the line compared with some numerical results from different groups. It shows a quite a good agreement. So this was the work back in 2000, almost 20 years ago. And in about 10 years before, we restarted this problem with some more rigorous math. So here we didn't use any assumption, approximation. We just started from energy conservation and start from Green-Coburn formula to calculate the thermal conductivity. And then we got an identity or a equation. So on the left hand, we have the information for diffusion because this is a mean square displacement. And on the right-hand side, we have CT, which is a heat flux correlation function. When you get integration for the CT, you got the thermal conductivity. So this is a connection between diffusion in general case and the thermal conductivity. So from that one, if we have a divergent thermal conductivity like this, and we got a divergent thermal conductivity with this one, and the beta is alpha minus 1. So this, so far we got two formula. So this has puzzled me for about 10 years. And in 2020, another group from Tsinghua University, they study from this fractional differential Fokker-Planck equation. They have unified these two formula. So the study the keys and found that these two formula beta equals to 2 minus 2 divided by alpha, and the beta equal to alpha minus 1. It's for different situation. One for the equilibrium transport, another for the non-equilibrium transport. So another work in 2021, this is published in Physical Review E. They have get this enormous diffusion with the Nether's second law. I didn't know the details, but actually the conclusion here is interesting. So the thought that anomalous diffusion in, for example, like in FU model, is due to the Goldstone mode, which means omega, the dispersion relation omega proportional to the K with this divergent alpha. Alpha is a diffusion coefficient. So far, I have checked all our numerical simulation. I haven't obtained this relationship. So this is another puzzle with further study. So we have answered some questions. Well, there's still a question need to be answered. The first one is whether the divergent exponent is universal. If it is universal, whether the divergence exponent is 1/3 or 2/5. So another question is, what is underlying phonon scattering mechanism? Like ABU model is a full phonon scattering. So why the full phonon scattering induce this divergent thermal conductivity? So of course, the final question is, for a given Hamiltonian, what is necessary and sufficient condition of the Fourier slope? So so far, not many trying, but what I know is this proof, mathematical proof, that they have proved that in all temperature range, the nearest neighbor interaction potential Vx, if it is larger than Ux, and then you can get a temperature gradient, but they haven't yet reached the proof for the thermal conductivity. So far, it's 1D conduction. Now we move to the 2D material. So for 2D nonlinear analysis, there's some numerical calculation showing that thermal conductivity proportion to the logarithmic of the length, not the length, actually the size. Suppose the lattice is square 1 L times L. So the typical example of a 2D material is a single layer graphene. So this was the first experiment work by Raman technique, is 2008. So the merit thermal conductivity of graphene, single layer suspended graphene, is very high. It's around 5,000. So we know that this value has a problem. Actually, the true value is only about 2,000, because the Raman technique has a drawback. It's a fundamental drawback. Somehow it's about 2 times exaggerate for the thermal conductivity value. So we have a measured thermal conductivity by using the thermal bridge method, like this insert here. So we use put a single layer graphene on this thermal bridge. We heat up from one side, and heat goes through the single layer suspended graphene to the other side, and heat up this sensor. And we measure temperature increase of the sensor, and then we can measure the thermal conductivity. So this is our actually experiment work. We keep the width of the graphene at the 1 micrometer, and change the length from a few 100 nanometers to 10 micrometers. And we found actually this logarithmic divergent thermal conductivity. And this actually three set of experiment data is we assume, for example, the contact thermal resistance of the graphene with the bridge. This one is 5%, this one 10%, this 15%. So in all 3 cases, we have this very nice logarithmic divergence. And here is another, actually, we draw the kappa versus log L, and log kappa log L, and we can find that for the large L, we have a 1D behavior, because we keep the width is 1 micrometer. So when the length goes to bigger, so this have this 1D behavior. And for the small L, we have a very nice 2D behavior. And also some recent experiment work by using the other 2D materials like MOS2 and WS2 and WSE2. They use this as secular membrane from a monolayer to bilayer and trilayer. They also found this actually logarithmic divergence of the thermal conductivity. Yeah. So if this is suspended single layer graphene, so actually if we put a graphene on a substrate, like here we put in silicon oxide substrate, and then the thermal conductivity is a finite value. So numerically for the single layer suspended one, it diverges from 1,000 to almost to 2,000. If you get L changing from 500 nanometers to 2 micrometer and so on and so forth. But if for the suspended, on a substrate, because interaction of the substrate, the thermal conductivity is finite. So the reason is quite clear, because graphene, the main heat transport is due to the Z directions vibrational mode. So when you put it on a substrate, this mode has been hugely suppressed. So this is experiment work by Li Shi from UT Austin. So the measured thermal conductivity is around 230 something, which is very close to our numerical calculation. Yeah. So the separation of thermal conductivity of single layer graphene on substrate can be easily explained by the FK model, because it's on-site potential and the suppression of the low frequency mode. or zero frequency mode. Yeah. So I mean, the question is not yet completely solved. So people still try to understand what is the physical mechanism of suspended single layer graphene, why it has such a huge semiconductivity. So now there's one actually opinion in 2014 that two groups from Mazari in EPF here and from Gangchun MIT groups, they both published paper on Nature Communication, proposed the second salt mechanism. So the thought actually in one single layer graphene, there might exist the second salt, which is actually temperature wave. So, but so far we don't have any direct evidence for the second salt. So this actually direct second salt evidence was for example, in very low temperature. What this was actually the work published in last year in Science 2022 by Pan Jianwei's group. The measure this actually the first direct observation of the temperature wave in low temperature quantum system. There's another actually theory called hydrodynamic theory of phonons, which trying to explain, for example, many interesting experiment and numerical work for the very large semiconductivity. Recently, in working with Marguerite Monin groups in CU Boulder, we get actually kind of very interesting theory. We use actually define a viscosity for phonon gas, and we calculate the phonon gas versus, for example, the porosity of this 3D material. So we can get all different, for example, different data. Here we have 1, 2, 3, 4, 5, 6, 7 groups data from numerical work to experimental work in different time span more than 1 decade. So it seems like all the data lies on this curve. So for 2D material, another interesting thing is about the magic angle, because people have predicted and experimentally proved that in twisted bilayer graphene at an angle 1.208, there's a magic angle, because at this angle there exists a superconductivity. So this was reported in Nature in 2018. So and then we have calculated this thermoconductivity, how it changes at this angle 1.08. So we found it's an interesting phenomenon at 1.08. There's a drop of the thermoconductivity. So across this 0.18 degree, and the thermoconductivity increase a little bit and then further down. So overall, people observe this thermoconductivity going down when you change increase the twisted angle. And then at this 1.08 degree, you have a very deep. So this is very big, deep. I mean, the thermoconductivity drops is around 400 watt per meter per Kelvin. So which is measurable experimentally. And then this actually is, it doesn't change when you change the temperature from room temperature to 400 Kelvin to 500 Kelvin. So I think about to do this experiment to prove that. So this can be also explained by some scattering of the phonons due to the twisted graphene induce some stress redistribution. So I summarize the first part of 1D and 2D systems, the heat conduction. In 1D system, the heat conduction goes with the system length L, the power law divergent. In 2D is logarithm divergent. Now I have sometimes I will show you the heat conduction through the interface. So the most important thing is asymmetric interfacial thermal resistance. So Baowen, we know that when
you have about 10 minutes more.
Okay, I need only about 5 minutes. Thank you very much.
Thank you.
Thank you.
Thank you.
Yeah. So we know this Kapitsa resistance, which means that you have a heat goes through one material. Let's see the solid to liquid, and then you have a temperature jump here. So which means that we can this interface can introduce a temperature jump, which means you can define a resistance here, which is called Kapitsa resistance. This was discovered Kapitsa in solid and liquid helium. So of course, this thermal resistance can be extended to solid, and solid gas. So this is a big issue for now for electronic industry, for the battery, and so on and so forth. This is how big this is, about 1 billion 10 billion, sorry, 100 billion industries for the material. So this is a big issue to work out this thermal interfacial material to get heat out. As the physicists, we're more interested in the underlying science problem. So actually, in this paper in 1969, in Gerard Pollack's review of Kapitsa resistance, he has asked two questions. The first one is that is the thermal boundary resistance for energy flow of liquid helium into the solid the same as the liquid profile in the solid near the interface be measured in more detail. So this is actually why we jump to this interfacial thermal resistance. So in the first in 1999, the second one is in 1988, 89, and the third one published last year. So this has probably become more and more important, not only from fundamental research, but also for application. So the problem here in this field is that there's no general theory to get all the experiment data well explained. So the two well-known theories, acoustic mismatch theory, which is like the heat is due to acoustic wave, or phonons is due to it's like acoustic when you go through the one another material, the wave will be reflected. So and then you go to the acoustic mismatch theory. So if the surface and then the acoustic will be scattering in all directions, this is called a diffusive mismatch. So if you look at actually this is experiment one in the middle, and acoustic mismatch, this thermal interference resistance times T cubic, and then you can see that actually this between the acoustic mismatch theory and the diffusive mismatch theory, there are about 3 orders of 3 orders magnitude difference. And the experimental data in the middle. So for the low temperature case, which is more close to acoustic mismatch theory, this is also about 1 order different, 1 order of magnitude difference from the experiment. And at the high temperature, and you have 1 order magnitude difference from diffusive match theory. So this is our recent actually experiment work in nano letter. We calculate the interference thermal resistance between silicon and nickel silicide. So this is an experiment one. We measured about 500 million watt per square meter Kelvin. This is a conductance. It's not a resistance. So with the dynamic, diffusive mismatch theory, we obtain 325. So a huge difference. Yeah. So the first question from Pollack is the interfacial resistance, thermal resistance is symmetric. So our answer is no. So we have calculated this one for 2 coupled nonlinear oscillators, nonlinear oscillator lattices. The one left side is a Franco-Roma model, and the right side is Appio model. And we found numerically that this interfacial thermal resistance is asymmetric. The difference can be as large as 1,000, even 10,000 times. So this large interfacial thermal resistance induce asymmetric heat flow. This is actually the underlying mechanism for the heat rectifier. So this is actually the numerical work, and this previous one we calculated. We measured interfacial thermal resistance between silicon and nickel silicide, and then the black one is from nickel silicide to silicon. So the difference is quite big. You can see here about 30%. Yeah, and here we have also established a very nice, we call it electron beam heating method to get the temperature, measure the temperature near the interface very, very dense, which means we can measure temperature at any point as we want. So which is the spatial resolution is about 10 to 20 nanometers. So this answers the second question of a Pollack. Yeah. Okay, I'm almost done. So this actually the asymmetric heat flow. This has actually extended. We can use that one to build a thermal diode and semitransistor and thermal logic gate and so on and so forth. So this actually has laid the foundation for an emerging field called phononics. So which means we can build a kind of thermal phononic thermal device to control heat flow like we control electronic current. So we have actually two review articles for this field. The first one published more than 10 years ago in Review Modern Physics 2012. And then recently we have another one for the Chinese Physics B. We have a summarized advances in between 2012 to 2022. So this is a very active field, and there are many actually applications using bioengineering to control the heat in one direction. Yeah, there are also many actually interesting talks I haven't touched, including the machine learning, how to design the thermal materials, including the interfacial thermal materials. And we have also, for example, topological phonons or phonon Hall effect and chirophonons, quantum heat transport, and so on and so forth. Yeah, I just moved to Shenzhen officially this year. So I have more or less or have already a big group, about 20 people, or more than 20 people. So, and I'm also looking for more people. So have a young student and young postdoc and graduate. They are welcome to join my group. I have actually two parts. The first one is quantum phononics, and the second one is about phonon engineering and the thermal functional thermal materials. This is more emphasized on the materials, how to fabricate material and to be used for the heat dissipation and thermal management. And then the first one, the quantum phononics, is more fundamental on how to use phonons to do some quantum communication. Oh,
thank you very much for your beautiful talk. And I remember meeting you in Singapore in 2006, and these ideas were just your imagination at that point, and now they're real. So it is wonderful to see this progress and learn about your beautiful work. And we have time for questions now.
Thank you very much. You're welcome. You're welcome to at any time.
Do we have questions from the audience? Any questions? We have a question from Professor Gupta.
Yeah, I just had a small question on the 1D case. How do you model this? You just use the conduction equation, the heat conduction equation?
Heat conduction, yes, we put that one example for the lattice model or flat model.
Which one? Sorry, either one.
You may model the heat for one-dimensional or two-dimensional.
Either. You explain anyone, please. Two maybe.
Okay. For one-dimensional one is let me go back to the first slide. Yeah, it's like that. So we, for example, the one-dimensional case, we keep the two ends fixed, and on the first particle, actually you can put many particles actually in contacted with the high temperature thermos. On the right hand side is the seed. The last end fixed, and then you put, for example, several. I mean, the better you put several parts in with the low temperature device, and then when you, for example, can establish, for example, temperature gradient and then calculate the heat current. You can calculate the connectivity for each particle, and you can calculate heat current, and then with the heat current, and you can calculate, because they have a temperature gradient, and then you can calculate thermal conductivity.
And you can pull out the correct behavior.
Excuse me?
You can pull out the correct behavior this way, the observed behavior.
Yes, for the I didn't catch the last half sentence.
The observed behavior is matches, right? Both.
Oh yes, and then you can observe the different behaviors. Yes, yeah.
Thank you.
Okay, thank you very much. There's one more question.
I feel this has no practical application, but in 1D, you have a power law. In one dimension, you have a power law divergence. In two dimension, you have logarithmic. So do you have a critical dimension, fractal dimension between 1 and 2, where
it's a very good question. Very good question. So you can see 3 dimensions we have a finite thermal conductivity. divergent of, oh, sorry, it's convergent. And in 2D, we have logarithm, and in 1D, we have a power law. So we so far, I don't know. I haven't seen anything between power law and the logarithm. And also how to get something between logarithm and the 3D case. So this is a good question, how to, for example, I just actually gave a 3-hour lecture this morning here in Kunming. So there are some students ask this question, can we get a theory which can cover from the 1D, 2D to 3D? This is a very, very, very good question. So can we get a general theory, can unify this kind of semiconductor behavior from 1D to 2D to 3D, even to some fractional dimension? This is a very, very good question. No, so far there is no theory. So I hope you can do that.
Okay. I think we should probably break to go to the poster session and tea. And thank you very much, Professor Li, for a very stimulating and interesting talk. Thank you.
Thank you very much. Hope we can see each other sometime in the near future.
Yes.